All right. Thank you, everyone, for joining us on this special Oasis meeting. Today, we have Ryan Holmes joining us from the Bureau of Meteorology down in Australia, which is why we are having our meeting at 6 p.m. Eastern, 3 p.m. Pacific time, because the normal Oasis meeting would be at 2 a.m. in Sydney. So, thank you for joining us. Thank you, Ryan, for joining us as well. And today he will be talking about air-sea coupling feedbacks over tropical instability waves. So please, Ryan, feel free to start sharing your screen and take it away.
Okay. Thanks everyone for having me. It's great to be here. Just wanted to check, can you see my screen now?
Yes, yes, we can.
Okay, cool. Okay, so yeah, thank you very much for having me. I haven't attended this meeting before, but it's nice to be here. So I'm going to talk today about some work I did when I was at the University of Sydney. So I'm now at the Bureau of Meteorology in Sydney, but this was mainly work I did while I was at the University of Sydney, funded by an early career researcher fellowship from the Australian Research Council. And this was work I did with my collaborators, Lionel Renaud, Lisa Maillard, and Julien Boucherel, who are from Lagos in Toulouse in France. And so what I'm going to talk about today is air-sea coupling over tropical instability waves. So I'm showing here a high-resolution simulation of the eastern equatorial Pacific, and you can see these kind of westward propagating. So this is SST we're looking at, and you can see these westward propagating cusps in the SST. These are tropical instability waves. And I'm going to talk about these in the context of air-sea coupling. So this is, as far as I understand it, this community is a lot about air-sea fluxes. So we're going to talk about that. And the motivation is mainly understanding how models work. So this is really going to be very strictly in model space. Yeah. Okay, so the motivation is really on trying to understand where model biases in GCMs are coming from. So we know that GCMs do have problems, particularly in the tropical Pacific area, and this affects their ability to predict things like ENSO and also to project climate change in this region. So on the bottom here, I'm showing an example. We're looking at SST variability, the magnitude of that in observations from HADI SST. And in the bottom left here is from the Australian climate model, Access CM2, which was our contribution to the CMIP6 archive. And so you can clearly see there's some issues here. The magnitude of the variability, El Nino variability, is a bit too strong. And if you look at, say, a power spectrum, you'll actually see that the power spectrum is really focused in the model right around about 2 years. So it turns out that the ENSO in this model is very biennial. It tends to flip back and forth between El Nino and La Nina from 1 year to the next. So where are these biases coming from? Well, there's a bunch of different stuff, but the one I want to focus on here is the fact that models can only resolve what they can resolve, right? There's a limitation on their grid scale. So if we're looking at a Stommel diagram, for example, which is plotting spatial scale on the x-axis against temporal scale on the y-axis with a bunch of different processes, and there's all sorts of these kind of diagrams lying around. If you draw a box around what GCMs can explicitly resolve, it looks like something like up on the top right here. So anything above about 100 kilometers. And so you can see there's a whole pile of stuff that they're missing, things like internal waves, mixing, mesoscale eddies for these kind of large scale models. And the fact that these models aren't capturing these small scale processes and their effects on the large scale contributes to these biases. Now, one thing I wanted to point out here, and I guess this is a bit of a philosophical discussion, is I feel like in the literature, there's a lot of work on understanding what the details of some of these processes are. So there'll be studies in observations or using high resolution simulations or even down to LES or DNS simulations and theory, really trying to understand the details of how these processes work. What I see as a bit of a gap, at least definitely in Australia and somewhat in other areas, is there's a lot less work on actually quantifying what the impact of those small scales is on the large scale. And this is what I would call rectification, and I'll talk about that throughout this kind of talk. It's difficult to do, but it's really important because you really want, at least for this motivation, for understanding why these models are biased, is you really want to understand what the impact of the small scales is on the large scale, because if you're missing that, you'll miss that impact. And then secondly, I also think there's a lot of there's not as much work, and this is again because it's quite difficult to do, in developing and implementing parameterizations for those processes that we do find have a strong rectification effect. And an example I like to bring up, I've worked a lot on ocean mixing in the past. I think when you look at the CMET5 and CMET6 models, about half of them are still using KPP. So this is an ocean mixing model scheme. It was developed in the 90s, and a lot of them are still using that without really much modification, despite there being some known issues with it. And there's obviously a lot of work in this area and a lot of models that are moving forward, but I think it's slower than it could be, I guess I would say. And I'll just point out, these are not easy problems to deal with. Okay, so in the context of this talk, we're talking about tropical instability waves. So as I mentioned, these are eddies that grow from equatorial current instabilities on either side of the cold tongue. So you have these kind of the EUC, the SEC surface current, the NECC. You have barotropic shear instabilities between this, and then you also have your kind of baroclinic standard instabilities that lead rise to these eddies. The most people mostly talk about them being important due to their lateral heat fluxes. So you can see they basically act, and we'll talk about this in a second, to mix heat from the higher latitudes where the temperatures are warm towards the cold tongue, and that acts to heat the cold tongue by up to about 1 degree Celsius per month. And that, if you compare it to other sources in the heat budget, is kind of comparable to the rate of atmospheric heating you have in some seasons in this region. An important point is that they're state dependent. So during La Nina events, you have much stronger currents, much stronger instabilities, and therefore much stronger tropical instability waves. And they act to damp those La Nina events by fluxing heat towards the equator and warming up the cold tongue that's anomalously cold during a La Nina event. Whereas during an El Nino event, currents are weak, you have really weak tropical instability waves, so they don't really do much. And so they've been thought to contribute to the asymmetry in the ENSO cycle, the fact that they damp La Nina events but don't do anything during El Nino events, which contributes to the fact that our El Nino events are generally can be stronger than La Nina events. And then finally, they're not particularly well resolved by 1 degree ocean models. This particular study showed that TW heating increases by about 40% when you go to a 1/4 degree model. Got to be a bit careful with that comparison because you're changing other things. So yeah, they're a bit challenging to resolve. They're much easier to resolve than mid-latitude mesoscales, and 1/4 degree is not something that's difficult to achieve nowadays in global climate models. So keep that in mind. Okay, now I wanted to bring up this, when I was preparing this talk, it's been a while since I thought about this stuff, and I went back to this paper that I really liked from 2006 by Marcus Joachim. And so I think this paper made a really interesting point, which hasn't really been followed up in too much detail in the literature. So basically what these guys did was they did a sea surface temperature budget in the equatorial Pacific and split that kind of budget into different processes that contribute to determining the up ocean heat content. So you have things like atmospheric heating, that's obviously a warming term in this region. You have things like entrainment, so like vertical mixing, and also mean upwelling here, which is a negative term. And then you have the kind of the interesting terms for this context is these two eddy heating terms. So you have a meridional and a zonal eddy heating term here. So these are the TRW, basically the role of the TRWs. And they pointed out two really interesting things here. The first one, which is quite interesting, is the fact that the zonal eddy heating term is quite large. So that's interesting because you typically think of eddies as driving heat fluxes by mixing heat down a mean gradient, right? But there's very weak zonal mean temperature gradient in this region. And so it's quite interesting that you get a significant warming from zonal processes, which is not coming from mixing heat down a mean gradient. So that's quite interesting. And then the other thing that they pointed out is that these eddy heating terms are positive in basically the whole region here, right? So again, this suggests they're not just mixing heat, because if they're fluxing heat from one location to another, you'd expect those regions where they're fluxing heat away from to be cooling. And so it suggests they're not typical kind of mixing length argument, doesn't really apply to these TWs. And the implication is there's this strongly link with vertical processes, basically. TW lateral heating is strongly linked to variations in the surface fluxes, surface air-sea heat fluxes, and also vertical mixing and entrainment. And as I mentioned, it also suggests that you're not going to be able to parameterize these things if you did want to, using kind of a down gradient eddy closure. So we'll come back to that as we go in through the talk. Okay, so the main motivation for this work was trying to understand what the role of air-sea coupling over TWs here. So I'm going to give a bit of an introduction to what I mean by air-sea coupling, particularly over mesoscale eddies. So this is, we're thinking in the context of both mid-latitude and equatorial here. So I split these kind of air-sea coupling processes into two classes. We have thermal feedbacks. So that's what I would call is linked to the SST anomalies associated with the eddies, and then current feedbacks, which is less associated with the surface current anomalies. So thermal feedbacks, one of the early studies on this was from Dudley Chelton in 2001, looking at satellite data here. So this is looking at sea surface temperature image and then quick scat wind stress magnitude. And so you can see if you look closely that you have stronger wind stress magnitudes over the cold SST anomalies associated with TWs. And this is basically because of changes in the stability of the atmosphere above the SST anomalies. Now, these feedbacks can get pretty complicated, and there's a lot of factors, and I'm not going to talk about them all. I'll just talk about a couple of them. Here's a schematic of one kind of particular situation that could be happening from this review paper in 2023. So let's say we have some atmospheric flow that's moving from a cool SST region to a warm SST region. Say this is a warm eddy here. What you're going to have is you're going to have a destabilization of the atmospheric boundary layer above those warm SSTs. You're going to get things like cloud formation of secondary circulations. And I guess key for this talk, the one I'm going to focus on, is the fact that you get weaker shear in the atmospheric winds here, basically because you have more mixing within the atmospheric boundary layer. And so that means you basically have you tend to get a stronger surface wind speed over warm SST anomalies. Now, for this paper, I ended up splitting these thermal feedbacks into two pathways. I'm going to take a little bit of time to go through here. So ultimately, the thermal feedbacks, they come from the fact that the surface air-sea fluxes depend on the SST. So taking the sensible heat flux as an example, I've written that down here. That depends on a couple of coefficients, the absolute value or the wind speed difference, basically the magnitude of the difference between the atmospheric wind speed and the surface current here, and then the difference between the SST and the air temperature. And so basically, if you have a warm SST anomaly, you're going to lose more heat above that anomaly because of the direct dependence of this heat flux on the SST. And the same kind of goes for the latent heat flux. Now, that has a few subsequent effects. So that's what I'm going to call a direct effect. But you can think about a couple of subsequent, more indirect effects. So, for example, that increased heat loss over this SST is going to warm up the atmosphere above, which is going to result in an increase in the air temperature, which is actually going to act against that heat flux anomaly. Another one that's really important is, as I mentioned over here, you get an increase in the surface wind speed over warm SST anomalies, and that results again in increased heat loss above warm SST anomalies. And so you end up getting kind of a net effect that looks like this. And then there will be subsequent feedbacks through the circulation that we're going to talk about today. So that's the heat flux pathway. We also have a momentum flux pathway. So again, because over warm SSTs, you tend to get stronger surface wind speeds, you also get a stronger surface stress. And so that acts through the surface stress there. And then both these feedback on other parts of the circulation, which is what we're going to look at today. The second one is current feedbacks. This is a little bit simpler. Basically, this is related to the fact that the surface stress really should be, well, the way it's computed is depending on the difference between the atmospheric wind speed and the current velocity. And it turns out if you were to compute, so this dot product here, this is known as the eddy wind work, or it's related to the eddy wind work. And as you can see, because of this negative sign here, this is always negative associated with the current feedback. And so that basically means that this current feedback is fluxing kinetic energy out of the ocean. And it's particularly well known in regions of the mesoscales in the mid-latitudes. It's known as the eddy killing effect. So an example here is from this paper in 2020. If you compare a simulation with and without this effect, when you include the current feedback, you get a significant decrease in eddy kinetic energy in our kind of dominant eddy regions. And this reaches about 30% on order in the mid-latitudes. And then that has subsequent effects on the mean currents. So again, from my co-author Lionel, this is looking at the Agulhas current. And you can see when you have the current feedback, you actually, what ends up happening is you reduce the size of the eddies, which actually means they extract less energy from the mean flow, which means the mean flow tends to stabilize a little bit. And so in this case, you kind of get a larger retroflexion in the Agulhas current. Okay, So the key question for this study is understanding how these feedbacks rectify onto the mean state, so onto the large-scale circulation, onto things like the mean SST or the strength of the equatorial currents. So the work on that, I'll just summarize this in a couple of dot points. So in the mid-latitudes, as I mentioned, eddy killing associated with current feedback is known to decrease EKE by about 30%, and then that subsequently impacts the mean flows. The thermal feedback's a little less well known. They're thought to damp eddy SSTs, and I'll talk about that in more detail. That damping effect is about 10%. And then there's a few kind of subsequent effects that I'm not going to talk about in detail, but in the mid-latitudes, and this is kind of an important point to make, they're not thought to be particularly significant. These, for example, the momentum flux pathway that I talked about, the fact that the thermal feedback impacts the surface stress, is not thought to be particularly coherent with the currents, and so you don't get an overall big impact. But we'll see whether that holds true in the equatorial region. So as far as past work in the equatorial region, same thing with eddy killing. So Justin Small in 2009 showed you get a similar eddy killing effect, which in this study he thought was comparable to the size of the kind of baroclinic barotropic conversion rates in the eddy kinetic energy budget. But saw some compensation with the large scale current feedback. And actually that's something I didn't mention. In the mid-latitudes, a lot of the conversation recently is about the small scale current feedback, but there's also current feedback acting on the large scale currents, and we'll look at that here as well. And then the thermal feedback, again, a little less work done on a few studies. Some of them suggest that the effects of these thermal feedbacks may be larger in the tropics than in the mid-latitudes. That you can kind of conceptually understand as the fact that SST has a kind of a larger impact on the atmosphere in the tropics than at mid-latitudes. And we'll see that in our study. And an example of that, this is again from one of Justin Small's papers. If you correlate mesoscale filtered wind speed and SST, this equatorial region in the Eastern Pacific where the TLWs are really comes out as a strong signature there. So again, suggesting this could be important in that region. Okay, so I guess the open questions that we wanted to address in this study is, firstly, what is the net impact of thermal feedbacks on the large-scale circulation, the equatorial region, things like ENSO? So again, that's the rectification effect of these feedbacks. And then secondly, what are the separate impacts of the large-scale and the small-scale current feedbacks? In the equatorial region, we have quite strong zonal surface currents and relatively weak surface winds. So we might expect that the large-scale current feedback would be significant and particularly larger than its effects in the mid-latitude. And I guess one thing to point out here is that a lot of the past work that's been done on these kind of questions has relied on diagnostic analysis. So looking at observations or looking at high-resolution simulations without doing experiments. And in that case, you can't really attribute causality. You don't really know what the rectification effect of those small scales here. And so really our approach here is we're going to put together some experiments where we can turn on and off these key feedbacks without changing anything else, and then have those effects kind of propagate through the system, and we can end up computing what the rectification effect is. Okay, so into the results. Well, firstly, our modeling approach. Basically what we did is we took a regional coupled model of the Eastern Pacific here. So it's a 14th of a degree ocean model, plenty high enough to resolve TLWs, and a 1/4 degree atmospheric model coupled together with the OASIS coupler. I mentioned that just because that's how we actually do our experiments, by manipulating those coupling. We've got a control simulation, so just showing a time series here. The top one here is Nino 3.4 SST. Basically, we have a control simulation. We spun up the model by repeating 2014, and then we run through from the beginning of 2014 to the end of 2019. And all the analysis here is based on the 4 years from between 2015 and 2019. I won't talk much about model validation. It's a coupled model constrained by the boundary conditions, but nevertheless, there are some significant biases. So you can see, for example, the dotted line here is the observed SST. The solid is the control simulation. You can see the variability is a bit weak. And I guess an important point to point out here is as well is that the TLWs in this simulation are also a bit weak compared to observations by about a factor of 2 if you look at SST variance. So that's important to keep in mind going forward. And yeah, we're doing some ensembles just to deal with kind of stochastic variability. Okay, so our perturbation experiments. Basically, we have 3 sets of perturbation experiments. The one that I'm mainly going to talk about here is what I call a no thermal feedback simulation. And basically what we do is at every single time step of the model, let's say the ocean SST looks like this field here. What we do is we smooth that SST so that the atmosphere sees a smooth version of the SST. And we do that only in the equatorial region. And we do it with a longitude-based filter. So we're not actually, and this is a key difference to previous studies, in the mid-latitudes, they use isotropic filters. The problem with that in the equatorial region is if you do that, you end up smoothing the whole structure of the cold time, which you don't really want to do. So we're basically just smoothing it so we get rid of those TRW signatures. And that's the only thing we change in that experiment. It's just that the atmosphere sees a smooth version of the SST at every time step. We also have some current feedback experiments, and we have 2 of these. This is in order to separate those small scale and large scale effects. We have a no mesoscale current feedback. So in this case, the surface stress is computed from a smooth version of the surface currents. And then we also have a third one, which is a no current feedback, where we just ignore the surface current when we're computing the surface stress. Okay, so I have a few slides and results and then a little bit of discussion at the end. So firstly, looking at the surface fluxes, we're going to focus on the thermal feedback experiment. So that's what TFB here is. We have 2 columns here. These are just a single time slice looking at the net air-sea heat flux at the top. So red indicates heat going into the ocean. The sensible component of that, and note the scale difference here, and then the latent component here. So latent heat flux, losing heat from the ocean. And then this is from the control experiment, which is fully coupled, and then the right where the atmosphere is seeing a smooth version of the SST. And so the air-sea heat fluxes in this case are computed in the atmospheric model, right? So in the case on the right, those air-sea heat fluxes are computed without the inclusion of the TW SST anomalies. And you can see that in the simulation. So you can see in the sensible heat flux, you can see the signature of the TWs in the control, but you can't in the no meso TFB experiment. The key point there is, particularly if we look at latent heat fluxes, these are TW cold cusps here. There's reduced latent heat loss over the cold cusps, increased latent heat loss over the warm SSTs. And that's the key point. So let's do a quick scaling calculation. If we look at the kind of size of these anomalies, we've got anomalies of about 100 watts per square meter across these TWs, just approximately. If this is acting into a 30-meter mixed layer, approximately, you can compute a temperature change from that, which is about a 2 degrees Celsius change in about 1 month. So that's really significant, actually. It's comparable. So the TWs are moving about one of their wavelengths in about a month, and the SST anomalies are about 2 degrees Celsius. So what you're seeing is that the air-sea flux variations from TW to TW are actually large enough to damp the TW's SST anomaly on the same scale as it takes to propagate one wavelength. And so thinking back to that little slide I had about Marcus Joachim's work, that really suggests that's really significant. There's a strong interaction between the lateral processes that the TWs are driving and those surface air-sea heat fluxes, and also vertical mixing. And just a side note here, we also did some ocean-only simulations, and in ocean-only simulations, you get some other issues. So for example, if you look at the sensible heat flux, you can actually see it's positive here. So this is a sensible heat flux going into the ocean, which is not really what we'd expect. And that's basically because the ocean-only simulation, the atmosphere above it has seen a different sequence of TWs than the TWs that are actually in the simulation. So you get some inconsistencies there. Okay, so now let's go on to the kind of net impacts of these feedbacks on the circulation. So firstly, looking at the impact on the TW amplitude here. So it turns out that what I'm plotting here, it's a little bit confusing. So I'm taking the control simulation minus the no meso TFB simulation. And so that's just the flip in sign there is just to say that this is the effect of the thermal feedback, which is active in control and not active in no meso TFB. So the blue here indicates that the thermal feedback is reducing the variance of SST, the TW variance of SST. And it turns out, depending on where you average, that reaches about a factor of 2. So basically the thermal feedback is damping the TW SST variance by about a factor of 2. The reason for that is one way you can understand it is through a air-sea EPE flux or an APE flux out of the ocean. And don't worry too much about the constants here, but the key point here is this depends on correlations between SST anomalies and air-sea heat flux anomalies. And so that's what I'm showing on the right panel here. So in the control, this being negative indicates it's damping SST anomalies. That's pretty significant. When we turn that thermal feedback off, we smooth the SSTs, which means we smooth the air-sea heat fluxes. That damping kind of completely disappears. Okay, it's a little bit more complicated than that, however, because there's a bunch of different stuff going on here, as I mentioned earlier. And we can actually play some tricks and do some filtering to actually kind of decompose this damping effect into the components due to the direct effect, due to changes in air temperature, due to changes in surface wind speed. And when we do that, what we find is that about a 75% of the damping is due directly to the SST dependence here. About 35% is due to those changes in surface wind speed, so the coefficient at the front here. And I'll just point out that's pretty significant. In the mid-latitudes, this number is thought to be about 10%. So again, indicating in the tropics, you have a stronger coupling with the atmosphere, you have kind of a stronger impacts in this region. And then you have about a 10% compensation. So you'll notice these two add to 110%. 10% compensation by the fact that you're warming up the air temperature above these warm SST anomalies, which kind of acts back in the other direction. Now, what does this subsequently do? One of the things it does is actually induce a damping of the eddy kinetic energy. And this, if you look at the eddy kinetic energy budget, which I'm not going to show here, is due to decreased baroclinic production, basically because B prime, so if it's W prime, B prime, that term, B prime reduces because the SST variance is reduced. 6% is not that strong. And I'll just point out that the eddy windwork changes are pretty minimal overall, at least in an average sense. They actually do change quite a lot at given latitudes, but when you average over a region, they don't change too much. Okay, finally, the main thing we're interested in here is the rectification effects. What are the effects of these on the large-scale circulation? So basically what we see is we decrease the TRW temperature variance, we decrease the EKE, decrease TRW-related heat fluxes, and this changes the mean SST, but it's pretty weak. So we see about a cooling of about 0.1 degrees Celsius, depending on where you look, in the equatorial region, again, because we're getting less heat flux towards that region. Associated with that, we get some reduced equatorial wind speed, again, just because of the fact that the mean SST is weaker, stabilizes the atmospheric boundary layer a little bit, so you get a stronger wind shear. We get some minor changes in atmospheric circulation, so we get a slight shift of the ITCZ towards the south and some slight changes in rainfall. But overall, I would say that the mean state changes we see are pretty weak. They're not actually that significant. And I'll come back right at the end to talk about why that might be. Okay, I'll talk very briefly also about the current feedback. So looking at the no meso CFB experiment. So this is, again, when I say eddy killing here, I'm talking about the small scale current feedbacks. This is really the current feedback acting at the TW scales. And when we turn that on, which is what's the case in the control, we see a reduction in an EKE of about 20%. That's just the typical thing that we've seen in the mid-latitudes that's associated with the eddy windwork. I guess more interesting in this context is looking now at the large-scale effects. So if we go to the no CFB experiment, that now has the effects of both the small-scale current feedback and the large-scale current feedback. So the fact that the current feedback acting on the mean surface equatorial currents extracts energy from those currents. And in that case, we see a more significant change. So we see about a further 10% reduction in air kinetic energy. And you can understand that basically you're extracting a bit of energy from the mean currents. Therefore, those zonal mean currents have reduced shears. They're driving less conversion. And so there's less energy there to convert to tropical instability wave kinetic energy through, say, meridional shear production. And so that accounts for an additional 10%. So interestingly, we end up with this similar number. If you remember, I mentioned it was about 30% in the mid-latitudes, the effect of the current feedback. We end up with a similar number here, except in this case, only about 2/3 of it is due directly to the eddy killing effect, and another third of it is due to this large-scale current feedback, which is definitely not the case in the mid-latitudes, where wind speeds are generally higher and the surface currents are generally, or at least the large-scale surface currents are generally a bit weaker. Okay, going on to the mean state. Again, relatively modest changes in mean state. If you just look at the SST panels here, so this is SST changes in those two experiments, you see some larger changes in the large scale case, again, because we've changed the strength of those zonal currents by extracting energy from them, and that changes zonal advection. So for example, the south equatorial current advecting cold water from the east to the west. That reduces a little bit, so you get some warming in the western part of the domain. And associated with that, you get some kind of changes in wind speed, as well as directly from the current feedback in those cases. Okay, so I'm at about a half an hour. I'm going to finish here. I'll just finish with a few thoughts and a summary. So I guess we started with this premise that TWs impact tropical Pacific climate and may be involved in or related to biases in global climate models. And we also know that they're strongly impacted and impact the air sea fluxes. That interesting paper by Marcus Yoakum, I think, is a good case for that. What we've done here is perform some experiments that isolate the rectification effect of these air sea coupling. I could run you through the results. There's some interesting differences, but I guess the main thing that I would like you to take out of this, or at least the kind of main result that we were looking for, is that we found that the effect of the rectification effect on the mean state was pretty modest in these experiments. Now, that could be because it's modest in reality, but there's also a couple of factors that mean that it's possible that it could be larger in reality than in our simulations. I've listed 3 here. So one, if you remember, I mentioned that the TWs are a bit weak in these simulations compared to observations. So that would also reduce the rectification effect of any of these modifications. Our changes in mean state are also constrained by our boundary conditions. So we have a regional domain, which is just in the Eastern Pacific. That was a very specific choice, because if we actually make our domain large enough to include the whole Pacific, we're actually going to get El Nino or ENSO dynamics within the domain, which makes it much harder to actually attribute causality when you're changing things. You have to run much longer simulations, much more difficult to deal with. So that's a possible condition. Basically, you can't change the mean state too much because it's constrained by the boundary conditions. And then finally, the time period that we looked at included the 2015-2016 El Nino event, where TWs were pretty weak. So again, we expect these effects to be stronger during La Nina events. So that's a summary of the work. I also wanted to finish on a couple of comments, which I think that there's lots of process studies on small scales, but I think there's less work. There is some work, obviously, in this area, but I think there's less work on quantifying the rectification effect of many of these small scales, which is really if you're interested in fixing model biases, that's really what you're interested in. And then secondly, designing, implementing, and testing parameterizations or improving parameterizations. And again, these are difficult problems, particularly parameterizations. When you start including new things in models, you have all sorts of feedbacks going on, and what you changed didn't necessarily do what you expected. So I guess I would say that I think that it would be really nice to have a bit more of a focus on translation of a lot of this research into model development in order to kind of solve some of these global modeling problems that we have. And so with that, I'll leave it there. Thanks a lot for listening, and I'm happy to take any questions.
All right. Thank you so much, Ryan. What questions do we have for Ryan? Dan, you're raising your hand. Feel free to turn off your mic and ask a question.
Hey, Ryan. Good to see you. Awesome talk.
You too.
I just wanted to ask, so, you talk about the changes in variance kind of as a whole, and you focused a lot on TIVs. I was wondering if you looked at all on the kind of scale dependence of things, like where the variance is changing or covariance in scale, and if it's really just TIVs or if other scales are changing, and how that works. Sorry for the vague question, but hopefully...
No, it's a good question. I haven't looked at it. Yeah, so it is an interesting point, because my filtering, when I do my experiment, right, that doesn't just filter the TW scales, it filters everything at smaller scales as well. So you potentially have some effects there. Yeah, I guess I can't really answer quantitatively because I haven't looked at it, but I suspect it kind of all goes along with the TWs, right? When you reduce the TWs, you're going to reduce the small scales around TWs as well, just because of that's how the energetics kind of works. But yeah, it's a good question. And you could think about doing different experiments to look at that, changing the scale of your filtering. I know Lionel's done a bunch of simulations looking at the impact of what your filter choice is. It really matters for what you do. And it was critical for us that we had an anisotropic filter. But yeah, you could think about doing multiple different experiments to look at that.
Cool, thanks.
All right. Shikar, I hope I'm pronouncing your name correctly. Feel free to go ahead.
Hi. Hi. Thank you very much for the nice presentation. I had two questions. One is like when you sort this prime terms, are you calculating the prime terms from the spatial filtering that you are doing
Yes.
for like, okay. The next thing that I wanted to ask was like, without like even filtering, how much is the eddy variance in the temperature? So, yeah, in the control case, is it comparable to like by how much the eddy variance changes when we smooth out the ocean fields and then give to
the change, yeah. So the change is about a factor of 2. So I actually have the background field here, I think, in the contours. So yeah, I mean, in some regions, it's almost like it's a pretty significant change in variance, which I thought was quite interesting because, yeah, this in terms of SST variance, it's really significant. I guess it was interesting to me that change in SST variance didn't actually have as big a large scale effect as you'd think, right? A factor of 2 change in variance, but really weak changes in mean state. That was quite interesting to me. But yeah, in terms of the mean state, you can see here we got 0.2, 0.1. I guess this is degrees Celsius squared in terms of variance, and the changes are about, yeah, the color bar is the same extent as that. So yeah, I guess the bottom panel probably shows you that the best. These are the mean and the change.
Okay, yeah, thank you very much.
Any other questions for Ryan? We got no rush here. Yolanda.
Hi, yeah, nice talk. Thank you. I was wondering, you've got a 1/4 atmosphere, I guess, over the waves, and I wondered if you can go back to your movie or one of your images of the cusps. I'm just wondering what the scale of those are and, where you would expect to see these responses. I mean, they're also moving. So I don't know. Have you looked at sensitivity of the atmospheric boundary layer scales to the to these experiments to give the atmosphere a chance to even respond to the.
Yeah, so that's a good question. I haven't compared different atmospheric resolutions. However, I have looked at these effects in I think it was Axis. So we had a version of Axis CM2 with a 1/4 degree ocean, so it did a reasonable job of resolving TWs. But it had a relatively low resolution atmosphere. And when I looked at that, I could see that atmosphere, the wind speed variations that you expect over TWs that you see, for example, from scatterometry or in high resolution simulations, it really struggled to resolve those. Whereas when we went to a 1/4 degree here, I think we're doing a reasonable job. And actually, Lionel Renaud, my co-author, has done a few of those. They've used a tropical channel model and looked at a couple different resolutions there. And they suggested that a 1/4 degree atmospheric resolution should be good enough to get, particularly in this region, to get those modulations, right? But I guess that was part of the key motivation is if you're thinking about global climate models, even if you have a 1/4 degree ocean model, you might not have enough atmospheric resolution to actually resolve the variations that you'd expect over these eddies in the atmosphere.
Okay. Yeah. Thank you.
All right. Going back to Shikar, I saw you put your hand up first, and then we'll go to Brian.
Sorry, this is a mistake. I forgot to put my hand down.
Oh, it's okay. Okay, no worries. Brian.
Hey, Ryan. It's Frank.
Hi, Frank.
So you've talked about most of the ocean processes and response, and in particular the large-scale response being sort of modest. Have you looked at the larger-scale atmospheric response, and is there sort of any kind of restructuring of the ITCZ or something we might think of as outside the boundary layer that the atmosphere is seeing these processes active?
Yeah, so that's what we were really interested to see. That was what I was looking for, I guess, in the simulation. We did see some changes, but they were really small. So this was one example I showed. I guess this is just showing rainfall, and it's hard to know with the magnitude, but we see everything that's consistent with what we see in the mean SST change. It's basically, I wouldn't say there's anything more complicated than that. When you kind of cool the equator, you kind of move the intertropical convergence zone a little bit north, I guess, and you see some changes, but it's really minimal. It's like, I guess it's hard to tell from this panel, but we're talking about stuff that's even barely statistically significant. So I guess if you look at the shading here, this is rainfall. Those are kind of a 95% confidence interval from the 5 ensemble members, and you can see the changes are barely significant in rainfall. We did see some kind of I guess I would say that most of the changes were limited to the boundary layer, and I looked throughout the whole atmosphere. You saw some small changes, but they were barely significant overall. I would say.
Okay, thanks.
Yeah. So, again, partly that could be because of the boundary conditions, the constraint from the fact that we have a relatively small domain. That domain choice is something that's kind of important, right? But we just were limited because I just didn't. I mean, this is something I wanted to do in a subsequent study, but haven't been able to do is go for a larger domain. But you're going to have to deal with the fact that if you have a larger domain, you're going to have ENSO feedbacks within your domain, and things get much harder in that situation.
Okay, thanks.
Any other questions? If not, oh wait, go ahead. Sorry.
Can you hear me? Sorry.
Yep.
Yes, I can hear you.
Zoom challenged. Okay, there I am. Just to build off of what Frank said, Ryan, with this asymmetry and precipitation, I get that it's only a little bit significant at certain latitudes, but there is some evidence that the asymmetry, the global monsoon systems are really sensitive to the meridional SST distributions. And so even in the East Pacific is such a big anchor for SST anomalies hemisphere to hemisphere. And so I wonder whether for certain global climate implications like meridional SST gradients and their effect on monsoons, whether even this local change is somewhat significant for things like monsoonal variations that drastically affect land, even if they're only in one location. So it'd be interesting to know, since this is a global model, or did you just run this domain?
It's just this domain. Yeah.
Yeah. It'd just be interesting to know that there could be more downstream impacts related to that sensitivity. I don't know if you have the ability to look into that, but that's just an idea I had.
It would be great. I think what it would require is obviously a larger domain, so you could do it in a tropical channel. But the issue there is you're going to change this. So you're going to have a control, you're going to have a no thermal feedback simulation. And I think you're going to have to run it for quite a long time because you're going to have a lot of internal variability in there. And so if you actually want to come up with a robust difference between the two simulations, you're going to need a really long run. That's going to be expensive. So it's going to be a bit difficult to identify. But it's a good point that, it looks small, but it could be significant given how constrained it potentially is. And it brings me to another point, actually, that I meant to mention. So at UNSW here, where I was spent a lot of time in Sydney here, there's a few people who work on small-scale convection in the atmosphere, and they've done a lot of work on the aggregation of convection over these kind of small-scale SST anomalies. And so that's one thing I was actually really interested to see here was, if you have the small-scale SST variability where you don't have the small-scale SST variability, do you actually get any net impact, even without these large-scale circulation effects, on precipitation? I think there's some large-scale constraints there suggesting you maybe don't, but it was interesting to see. And I think another reason you might not see that is because the really strong rain band in general is actually further north than the TWs are. So there's not a direct spatial correlation between where you're changing the SST variance and where the strong rainfall in this region is. But yeah.
Dan, you have your hand up.
Sorry, this is like my second question, but that made me think of something. Ryan, can you go to the end where you say the like possible issue? You listed like those 3 possible issues at the.
Yeah.
Yeah, it was just when you were making those comments, I was wondering if, about the sort of smaller scale convective processes. I was wondering if you thought that the sort of framing of the parameterizations they tend to be kind of not super scale dependent in their formulation and formulated for these coarser resolution models. Is there any indication that the kind of framing of the small scale processes that are subgrid scale from the perspective of your model and the large scale model might cause you to get a weaker signal or a stronger signal in this? Is there some way you can assess that? Maybe that's just too hard of a question, but is that something you're concerned about? I don't see it mentioned here per se, but
yes. So
like
it's definitely something we did. It's definitely something we discussed when we set up the simulation. So I guess you're saying what is so one way you could do it is what is the sensitivity to the atmospheric convective parameterization that you have in this model? I'm not an atmospheric dynamicist, so I don't really know heaps about that kind of stuff. I know that Lionel's done some sensitivity studies, and they decided on the parameterization which we used in here, which I can't remember what the form was, because it was one of the best performing when they did some sensitivity studies. But yeah, I guess people in this region, when they talk about model biases, the 2 big things that they often talk about is atmospheric convective parameterizations and ocean mixing. And so there's probably quite a lot of uncertainty there due to those parameterizations, and that'll be impacting this. Yeah.
Let's go to Megan.
Yeah. Hi. Thanks. I'm kind of struggling a little bit to formulate my question, but okay. When you talk about rectification, you're really talking about an eddy mean flow kind of change in scales or a transfer of energy between scales in a way. And are you envisioning that these feedbacks are giving rise to kind of sharper and more energetic waves, or in the tropical instability wave? So if you think of the tropical instability as actually being the mean, and some of these feedbacks being kind of eddies on that background cuspy, what is the net effect then?
Well, in terms of the large scale, that was what this study was trying to answer. So I guess you mentioned eddy mean flow, so that's one way to think about rectification. I guess here I was thinking about it in a little bit more general sense of there's a small scale process. What happens if you turn it on and off? What is its kind of net effect when you pass through all the other feedbacks? And I think this way of setting up the simulation is a good way to kind of evaluate that. If you're going down to smaller scale, so yeah, you could imagine doing a similar kind of experiment, right? Where you use a much smaller filter, where you actually smooth out some of those sub-mesoscale, I guess, well, for want of a better term, because there's some issues with mesoscale and sub-mesoscale in the equatorial region. Let's call them sub-mesoscale. You could imagine a similar experiment where you used a much smaller filter to smooth out those sub-mesoscales or the SE feedbacks associated with those, and then looked at the effects of those on the TWs. And I know there's quite a lot of work, I guess, in the last 3 or 4 years looking at the sub-mesoscale SE coupling in other contexts. I haven't seen much in the equatorial region, I guess, or at least from the modeling perspective. But yeah, there's some suggestions those effects could be significant. Yeah, but I would expect overall. Yeah, sorry.
Well, you showed that slide where you had the T prime times a Q prime.
Yeah.
And that's in the, so that's the eddy fluxes affecting the eddy energy, right?
Yeah. Well, in this case, it's the air-sea flux modulation with TWs affecting the eddy SST. It's a term in the variance equation, the SST variance equation. Yeah.
But this is actually going to damp the variance, not increase the variance.
Yeah, definitely, because you're losing more heat over warm SST anomalies and gaining more over cold SST. So it's going to damp the variance because of that. It's basically, we think of it as a flux of eddy potential energy out of the ocean. And people like Justin Small and Stuart Bishop and Frank, who's on the call, have looked at this in global contexts and sensitivity to model resolution and stuff. So there's a lot of nice literature on that around.
Okay, thanks.
Billy.
Yes, yes, thanks. Nice talk.
Hi, Billy.
Hi. I'm interested in the difference between the southern and the northern hemisphere. And in the front of my mind is the Dudley Chelton paper that you showed a figure of that depended crucially on the direction of the background, or say the free atmosphere winds, in relation to the fronts. And so there's the effects of that, namely the convection in the boundary layer, mixing the boundary layer and increasing the wind speed, happen, I think, only on the northern side, where the wind is blowing from the cool to the warm water and that sharp front. So going back to what is the difference between the northern and southern hemisphere, because in that movie you showed, it's not a dramatically strong difference. And the fact that when you're, these whole experiments really don't depend on the direction of the background wind. I'm wondering if this is a way to understand more about why you have this very strong signal in the heat fluxes and all these damping processes in the north, but not in the south.
Yeah, so that's a good question. It gets kind of complicated. I guess, well, there's a few things I could say here. So one is you're right, in particular in terms of the thermal feedback effects on the eddies, on the momentum flux pathway. So that's what actually Sarah looked at in 2007. So I have this schematic in the top right here. And it gets complicated. You're thinking about the direction of the mean wind, that impacts what the effect of that is on the eddy wind work. And we saw similar effects in our simulations. I'm not going to go through them in much detail. However, I think in terms of the SST, so there might be some correlation with the velocities here, but in terms of the SST anomalies, I still think this is the same in the northern and the southern hemisphere, because you're thinking about TW-driven SST anomalies. So you have a warm anomaly and a cold anomaly. The mean direction of the wind, well, there's a bit of change in the direction of the wind. But I still think this will be similar in terms of the TW effect in the northern and southern hemisphere. And so I guess that said, what I suspect is most of the reason for the asymmetry in what we see, like let's say this one, you can see the changes in SST variance are stronger in the northern hemisphere. I suspect most of that's just tied up in the fact that the TWs are stronger in the northern hemisphere, right? Everything's kind of scaled by the strength of the TWs. You're going to get stronger changes where the TWs themselves are stronger. But yeah, it would be interesting to think about that in a little bit more detail. Try and divide that up. And you're exactly right that there's some important effects of the fact that there's a mean wind in a particular direction, and the way that interacts with the SSTs, and the way particularly the way that the wind stress anomalies associated with that project onto the ocean's surface velocities, which is how you get changes in eddy wind work and how you get direct changes in the eddy kinetic energy from that. Does that make sense?
Yes. Maybe I'm ignorant on this topic, but it seems to me that it's much easier to, through convection, mix momentum downward into the boundary layer, that is going from cold to warm, than it is going from warm-ish to cool, where you have to stabilize the boundary layer, and that those things are not necessarily symmetric.
Okay. Yeah. No, that's a good point. Yeah. Yeah. I could see that could have an impact. Yeah. I imagine it would be tricky to decompose in this kind of a situation. But yeah, that'd be interesting to think about in more detail.
Thanks.
Thanks, Billy.
All right. Before we go, last question here was in the chat from Brian. They wanted to know that paper that you're showing on your summary slide, is that published? And where can we find it?
It just came out in JPO on Monday. So yeah, JPO, if you Google the title, you'll find it. Yeah, I should have put a link here, but yeah, it should be pretty easy to find. I think it came out in the Monday issue of JPO. So good timing.
Excellent. All right. We've got one last question here from Nicholas.
Yeah, thank you for the talk. Very nice. I just have one question regarding really how you do the filtering.
Yeah.
Do you filter the net fluxes, or do you filter the components of air temperature, wind that go into the net fluxes?
Great question. In this situation, we're filtering the SST directly. So basically, there's what's passed between the ocean and the atmosphere through OASIS is the surface currents and the SST. So you basically pass the SST from the ocean into the atmosphere, and then the atmosphere does its stuff in terms of computing the heat fluxes. So it just basically computes its heat fluxes, its surface heat fluxes, from a smooth version of the SST. However, that said, we did actually design a bunch of experiments where we wanted to do the same thing back in the other direction. So what happens if I guess what I was saying there is passing stuff from the ocean to the atmosphere. So what do you pass from the atmosphere back to the ocean? You pass the heat fluxes back. So you could think of an alternative experiment where you smooth the fluxes after they've been computed from the atmosphere back into the ocean. And I think that gets at some of the different aspects of the coupling. We didn't actually end up doing those experiments because basically I changed jobs and moved somewhere else. But it would have been really interesting to kind of look at that. But yeah, in terms of these experiments, we just smooth the SST as it's passed to the atmosphere, and then the atmosphere computes all its fluxes from just a smoothed SST.
Okay, great. Thanks. Thank you.
All right. With that, since it's almost 7 p.m. out here on the East Coast and 10 a.m. for you, Sydney, I think we can go ahead and wrap this up. So thank you again, Ryan, for taking the time. Thank you to everyone to being flexible with the new time for the seminar. There's no meeting next week, a reminder, so we'll be back here again on October 29th. So thank you again.
Thanks a lot for having me. See you all later.
Thanks, Ryan. Bye.